on this computer. Okay, go ahead.
Okay, well, yes, thank you, Wilson, for the introduction. I forgot to write in the title that this is part 2 of my talk. In the part 1, I explained with some technical details, what a Mumford curve is and the parts that are important for this talk. And this talk will be more about the analysis. So if you were not there last time, I think it will be possible to understand what I'm saying, even with just a short summary of last time. Okay, so first of all, an introduction, and then we'll pick up some more notation, and I will summarize then what we have learned in part 1. And then we come to the analytic part, which is namely a p-adic, or p-adic if you like, to stay in the p-adic numbers dictionary. And then we come to the heat equations, first associated with affinoid coverings, and then heat equations on Mumford curves. And then in the end, a conclusion, acknowledgements, and 2 references. First of all, the plan now is to construct a heat operator on a Mumford curve of genus at least 1. And this construction generalizes an idea which Wilson published in a paper where he used p-adic methods on graphs. And for this reason, we need a graph belonging to the Mumford curve. Those of you who were there last time remember this will be a reduction graph or intersection graph. So, and then we need more general.
Patrick, there is a problem with the sound.
Is that better?
Yes, thank you.
Okay, and we need more general wavelets than those constructed by Sergei Kozyev. And in the end, in order to have everything work on a Mumford curve, we need to make everything periodic or even doubly periodic.
Patrick, sorry, again, the volume went down.
Okay. I don't know what's wrong with this, but anyway, I'll keep this here. Okay, let's see if I can move. No, I can't. Okay, so now notation K, we'll fix a local field, a non-Archimedean local field, K times its multiplicative group, and we have the valuation. OK is the unit ball, and then we fix the Haar measure in such a way that the unit ball has measure 1. Small k is the residue field. It has p to the f elements. F is just the degree of the residue field extension. And notice that the volume of a scaled ball by some power of the using the uniformizer pi of the unit ball will have measure p to the minus m times f, because you have this extra f here and there. And then we fix a lift from the residue field into the integers of k. Further, we fix an additive character of our local field into the complex numbers. And then sometimes when we integrate, we will write the Haar measure in the usual as dx, especially when using functions in x and such integrals. And then what we'll often need is an indicator function, and we will write it with an omega and write the variable and the set in such an intuitive way. X in u. You might be used to other notations where you just have balls, but our sets will not be balls, so we will have to write it in this way. And u is any measurable set. So what have we learned last time? We learned last time that a Mumford curve x over our field k is a smooth projective algebraic curve over the field k of genus G at least 1. Those of you who have done some p-adic mathematical physics can think of this as a p-adic Riemannian surface. And we learned that not all such algebraic curves are Mumford curves, only a special kind. And a Mumford curve is a rigid analytic space obtained by gluing finitely many so-called rational affinoid domains in the projective line, and these are known as hold disks. So you can think of those equations defining a disk with holes. and the corresponding spaces are a bit have more structure on them. They're glued together to form this Mumford curve or p-adic Riemannian surface. And a Mumford curve has a semi-stable reduction over the residue field whose irreducible components are rational curves or genus zero curves. And these form, you can make out of this a reduction graph. The vertices are the irreducible components and the edges are the double points. And you can do this with respect to a pure rational affine covering of the curve. And the first Betti number of this graph equals the genus of the curve x. And a Mumford curve has its k rational points now disjointly covered by holed disks in k. And it is of the form some covering space omega inside the projective line modulo where a Schottky group acts with G generators. That's what we learned last time, and we will use some of these things. So now we come to our p-adic dictionary. Pi is remember is a uniformizer playing the role of the prime number p in our local field k. We fix a set Z, which is compact, measurable, and then we have a finite disjoint covering of Z by sets of finite measure. We call this with this calligraphic U. And we look at the space of continuous functions written as CZ or CZC, continuous complex valued functions. And we have the bounded operators, bounded linear operators on a Banach space F. This time it's a complex valued Banach space. And n is the size, the number of patches in our covering, U, and we look at n times n matrices, but they will be indexed by U. So we can write this the matrix space as C to the power of U times U, and we will have a norm on this space for a matrix. We will write the norm, depending on U, as the square root of sum over, where you sum over all the patches in U, take the matrix entries valued, absolute norm squared, and weighted with the measure of U times the measure of V inside the square root. This defines a norm on the space of matrices. And here is our dictionary, this lemma, namely, there is an injective isometric homomorphism between algebras, C algebras, namely the n times n matrix or U times U matrices, I should write, and the bounded linear operators on this space of complex valued continuous functions on Z, where a matrix is given by an operator whose kernel, A of x, y, is this sum here with the indicator function. So you sum over all the patches in U and write down the matrix element AUV and multiply it with the indicator function x in U and y in V. And on the one hand, so isometric is because you use the norms. On the left-hand side, you have the U norm, which we had before, this one with the weights here given by the measures. And on the other hand, you have the operator norm given just by doubly integrating out the kernel squared, norm squared. And yeah, this is an injective isometric homomorphism. And we can do something similar for vectors, which will column vectors, which are indexed by U. So there's our functions from our covering into the complex numbers, and such a vector E is indexed by by patches V, and you make a function out of this by taking linear combinations of the corresponding indicator functions, where the weight is just EV, and then you normalize it with the measure of the set V, which you have used as an index inverse of the measure. And this is a continuous function. It's locally constant. And there is a map. We will call it again B, abuse of notation. We have this C to the U space mapping into the continuous functions on Z, where E, as such a vector, it just maps to this function. And there's an action of bounded linear operators on this space given by the usual integral using the kernel A of xy. And our lemma, which is part of the dictionary, is that, well, it doesn't matter which picture you use, you will get, if you take a matrix A and multiply it by a column vector E, and then map this into the other space of functions with a function B, you can do the same thing as multiplying in operator-wise B of A acting on B of E. And a corollary that you get is if you have an eigenvector E of a matrix A with eigenvalue lambda, then the mapping will be, you will make out of E an eigenfunction of the operator B of A with the same eigenvalue. And this will be useful when we want to study the spectrum of certain operators that we'll construct. So matrix and operator, they can be interchanged in a spectrum when you look at the spectrum. And now heat equations associated with affinoid coverings, so coverings by Holt disks. But first, let's recall Kozyrev wavelets. Remember, they form an eigenbasis of the Vladimирov operator, and they're supported on balls. And we want to generalize this. We want to have wavelets supported on compact closed open sets, and we want them to be eigenfunctions of certain pseudo-differential operators, and these pseudo-differential operators are supposed to generate Feller semigroups so that we have some Markov process and then solve the Cauchy problem for the corresponding heat equation. So wavelets first. We'll take our measurable set Z and fix some covering set of coverings, cov Z, a family of disjoint coverings of Z. This is a so-called Grothendieck topology of admissible coverings. So we don't want to allow any certain coverings are nice, and if they're disjoint, then
Patrick, there is again a problem with the volume. Sorry.
okay, thanks. So we want to have just a certain type of coverings, namely disjoint coverings. They satisfy the axiom of this Grothendieck topology, but if you don't know what this is, it doesn't matter. Important is we have disjoint coverings, and later actually disjoint coverings by the patches are Holt. And this set cov Z is partially ordered with refinement of coverings. And actually we want to have just certain type of refinements, namely strong. So a strict refinement is strong if no patch from one covering is in a patch in the other covering. So each patch gets split in the refinement into non-trivial sub pieces, disjoint sub pieces in that refining process. And then we have a strong maximal chain in cov Z. This is just a chain of such strong refinements. So in each step you have a strong refinement, and this chain cannot be strongly refined. And then you have a strong maximal chain of coverings. So we fix here our compact open set Z, and as I said, we want to have cov Z to be just disjoint coverings by Holt disks. And we define a C wavelet, where C is a strong maximal chain in this set of coverings. And a C wavelet on Z is a family of functions, C, indexed, well, by C, of course, but also by J and U. And U is a patch in U, in calligraphic U, and calligraphic U is one of those coverings in this family C. J is an element of the residue field, and then what you do is you take, well, what you usually do with Kozyrev wavelets, you take your character and write something inside of the character, namely x times tau of j. Tau is just you lift the residue field element into the local ring, okay, and then multiply with some power of p. I'll explain in a moment what power you use. And then multiply this character by the indicator function x in u, just imitating really Kozyrev wavelet, and then normalize it by the square root of the volume measure of u. So now this important is not this e. E comes from the field k. So it's a in a p-adic case, you have just the ramification degree of the field extension over QP. This is E. You will always have that in the denominator, but this D. D is describes the radius of the smallest hole that you have in your holed disk, U. And then this gives you your wavelet. If you take as an example, Z is the whole of QP. Okay, this is not compact, but it's locally compact, but it doesn't matter. And C, just the strong maximal chain of coverings in which each covering is given by the translates of a fixed ball inside of ZP. Then the C wavelets in QP are just the usual Koserow wavelets. The only thing that you have to take care is that you take the correct lift from the residue field FP into the ring ZP. Just J bar maps to J. And the results that you need in order to go on is vanishing of integrals, and that does happen. You integrate over your wavelet, you will get 0. Even if you put weights, namely distance between x minus y to the power of alpha, where x in z and w in c, that integral also vanishes. You can calculate this. This works. Now we can define our operator, namely fix such a covering in Cov Z, take a matrix, complex value matrix, indexed by U, and we call it the Vladimирov-Tableson operator associated with A and U is just the p-adic Laplace operator on L2Z given as, here you have a kernel function, and then the usual way times f of y minus f of x dx integrated over z. So this operator, and the kernel function is just, so you take pairs of indicator functions for each patch, x in u, y in v, multiply them with the matrix element AUV, but also with the distance between a point in u and a point in v, x minus to the power of alpha. And if the diagonal of the matrix is 0, then it becomes a function of just the patch u.
The volume went down. Sorry, Patrick.
Oh, sorry about that. I don't know what's happening. So the degree of u is, in this case, just the integral over where you fix u, or x in u. And so this becomes a sum over AUV, integral v times the distance between u and v, where v is summed over. Remember, right? Because x and y, because v and u are always disjoint because the diagonal element is 0, this will be a function which does not depend on x in u, but just on u. So the degree. And what we get is, well, it's almost for free, is a Zuniga type inequality. Namely, it just says that the bounded, and the bound is given here. What you have to require is that the matrix has only
The volume, Patrick, went down.
What you have to require is that the matrix has only non-negative real entries and the diagonal vanishes, and alpha is a real number. Then you get your bound first on Schwarz functions, but then by taking limits also on all of L2Z. And if AUV is symmetric and the matrix diagonal elements are 0, then this operator is self-adjoint. The proof is you calculate it one by one that is symmetric, first with the adjacency AU alpha, and then look at the diagonal, which is this using the Kronecker, the Dirac delta function. And because it's bounded, you can conclude that it's self-adjoint. And now we come to our theorem. Our first theorem, namely, if alpha is real and you fix a covering, disjoint covering of Z with whole disks, and take a U matrix A non-negative, symmetric, and vanishing diagonal, then take C a strong chain of admissible covering Z, so at the same time type, such that U in C is on top, and this chain C is strong and maximal with this property that U is on top, then the C wavelets, together with the functions coming from, well, these are just the function makings of eigenvectors of the graph Laplacian, whose adjacency matrix is given by AU times the distance between U and V to the power of alpha. And those eigenvectors are normalized to 1. These form an orthonormal basis of L2 of Z, consisting entirely of eigenfunctions of this operator. So the operator is diagonalized by two kinds of functions, namely by those wavelets and by functions coming from eigenfunctions of this matrix. We can prove this. First of all, you calculate this integral with this kernel A, where the wavelet is inside outside the integral. Inside, you can.
The volume, Patrick, went down again.
If the wavelet is inside, then you see that this integral that you have here vanishes. This because it's the property of our wavelet, and if it's outside, then you just find you're multiplying with the degree of U, and so the wavelet is an eigenfunction of our operator with eigenvalue of the negative degree of U. And so now the eigenvectors of this matrix B alpha, so these correspond by the dictionary to the operator corresponds to the Laplacian of the matrix B alpha, and this does not depend on the choices because the diagonal vanishes, so it's just the distances that occur between to the power of alpha between U and V. And so that means we have had the result that E of x, this function, is an eigenfunction of the operator if and only if vector E is an eigenvector of B alpha by the dictionary. That's the second part. And now the eigenbasis. Now the C wavelets here, they do form an orthonormal basis of this subspace of all functions, of all L2 functions, whose integral over each patch vanishes. That means you have an orthogonal decomposition over L2 space, where we'll look at the orthogonal complement. Namely, it will show that it's spanned by the functions coming from eigenvectors. Okay, that's this lemma. So the space spanned by those functions E of x coming from eigenvectors equals the orthogonal complement. First of all, this space is given by such functions, L2 functions, which are constant on each patch. And then you can show that this is inside the orthogonal complement, namely, well, you see that these are constant on each U, and then you integrate with a wavelet. Either the sets are disjoint, then it's zero anyway, but if it's a wavelet where the sets of these, where the local constancy is one in the other, then you have our fact of integrals over wavelets. The integral will vanish. So that's orthogonality. And on the other hand, if you have f in the orthogonal complement, then you take this function, sum over U and U, inverse weight, inverse volume, integral U f of x dx, indicator OX of U. This is an L2 function and it's constant on each U because it's an L1 function, and then you take the difference f minus h. This is an L2 function and it vanishes on each patch of U, and that means it is zero, and then you have the equality. So of those spaces. So this is the orthogonal decomposition. And a small example shows that, well, QP, U is this ball PZ, and V is the translate by one of this ball. Z is just the union of those disjoint balls, and U is the covering UV. Take this matrix, which interchanges, which jumps from one ball to the other, and you have then this kernel function and take Wn as just shrink this ball U by powers of n. Then you can take this wavelet, and this is always also an eigenfunction of the operator, and you have infinitely many. That means for this eigenvalue minus mu v, which happens to be the degree. So this shows that these operators are in general not compact operators, not even if alpha is 0. Now the Cauchy problem, in this case, where you have a compact Clopen set Z in Q, disjoint covering by whole disks, and now we look at CZ with the maximum or supremum norm, and an operator is positive if it maps non-negative real functions to non-negative functions, and you define a semigroup to be positive if for all t the operator, corresponding operator is positive, and you define operator satisfying the positive maximum principle if for all f in the domain and x0 in z you have, so the x0 is where the supremum is achieved of f of x in z, and if that's non-negative, then a acting on f at the point x0 is negative. Our important theorem here will be Yoshida-Hille. This tells you when do you have a Feller semigroup. I'll explain what a Feller semigroup is in a minute. But first, the closure A bar of a linear operator A on CZ is single valued and generates a strongly continuous positive contraction semigroup, or a Feller semigroup T of T on this space C of Z if the domain is dense in our function space, and if A satisfies the positive maximum principle, and if the resolvent set is dense in our function space for some lambda positive. Now, what is a Feller semigroup? So this is a family of bounded family of linear operators. Is a Feller semigroup if, well, you have the semigroup property first, and if for any function h in our continuous function on z, you have that pt of h approaches h with respect to the maximum norm for t going to 0. And third, if h, or function h, satisfies it's between 0 and 1, then pt of h will also.
The volume, Patrick.
Yeah. Now if you have a symmetric non-negative entry valued matrix with vanishing diagonal, then you have this operator epsilon times this dAu alpha for epsilon positive with alpha real. This generates a Feller semigroup, namely in the usual way exp te epsilon delta on our function space C of z. And Wilson's proof works here too. I'll sketch it. So you apply Yoshida-Hille. First, d alpha generates a semigroup called Qt, and it satisfies Yoshida-Hille, and then epsilon times this operator is a bounded linear operator on a Banach space, hence exp, the usual exp, is a uniformly continuous semigroup, and then you have that the infinite, you have to prove these things. Then the infinitesimal generators of the two semigroups agree, and that means the semigroups are equal. So this is, and you have proved the Feller property for one of those two, and that means it generates a Feller semigroup. Now we can formulate the Cauchy problem for a heat equation on Z, namely find a function such that this pseudo differential equation is satisfied. So time derivative just in first order minus epsilon times this operator d acting on a function h of t of x is 0, and the initial condition has to be satisfied. H of 0x is a fixed continuous function h0 of x on the space Z. And because the corresponding semigroup is Feller, this describes a p-adic heat equation on Z. And that means there is a p-adic diffusion process on Z attached to this pseudo-differential equation. And in fact, further, there exists a probability measure such that you actually do have a Markov process which generates the solutions of the Cauchy the differential equation, and the paths are right continuous and have no discontinuities other than jumps. And in fact, this is given by convolution with this function. Well, you write the lambda out in this way if you have, that's what you get if you just look at the operator. Now we do the same thing briefly on Mumford curves. We have done everything so far on a fundamental domain of the Mumford curve, and we will now have to make everything gamma invariant, where gamma is a Schottky group generated by G at least one hyperbolic Möbius transformations, and you have omega the complement of the closure of the limit points of gamma, and X, our curve, is the quotient space omega modulo gamma. And now you fix a fundamental domain for the gamma action, which is compact and closed open inside the k rational points of this omega. And then you fix a covering which is verticial. Verticial means that, well, you have an action on the Brouatitz tree and a part of the Brouatitz tree, and the vertices of these covers you can let these correspond to the patches which are disjoint. The edges do not they correspond to double points which are not part of the field K. So you have a disjoint covering by hold disks of this space F, and then your aim is make everything what we've done before gamma invariant. First of all, if you have a function on the fundamental domain, which we can write as a sum of indicator functions multiplied by some restriction of f and u, patch u, we're acting on an element x, and then you make a gamma periodic extension of this just by moving around this space u with your element from the Schottky group gamma, small gamma, this indicator here with gamma u, and translate it back then so you have a value to multiply it with. And this is a doubly periodic function. However, it's not L2 integrable in general. So for this reason, we have to introduce weights. We will use a weighted integral. If you have a gamma periodic function, then the integral symbol will have omega and s, a complex number, or a positive, real number greater than 1. And you integrate over each moving around, transformation of each patch. The weight will be m gamma u to the power of minus s, where m is just the maximum of 1 and the absolute value of the derivative of the transformation gamma on the patch u. So, and this makes integrals converge. This derivative comes from the transformation rule for integration, and then you integrate out what you divide over what you kill this transformation, because especially if the powers go up for powers of gamma, then you can have things not converge, and you cancel this with this m, as long as s is greater than 1. And then you define in a usual way an inner product, just the integration of f gamma times g gamma bar complex conjugation, which is this big sum, and make an index s in the symbol for the inner product. And then you can define the L2 functions with an index s. These are, of course, on the curve, or the gamma invariant functions on omega, L2 functions with index s greater than 1. These are the gamma periodic functions, such that this norm that you have from the inner product is finite. And so the norm is written here as the square root of the inner product of f with itself, indexed by s. And of course, the superscript gamma will indicate that you're talking about gamma invariant functions. So continuous functions will have these spaces too. We look at the invariant functions. A technical lemma which assures that you have a Hilbert space is that there are only finitely many Möbius transformations inside gamma, such that the absolute value of the derivative d prime acting on z takes a fixed value on a given small closed open set in K. The reason is the gamma is a discrete group, so there are only finite many such gamma, and then with this you can prove that this construction gives you a Hilbert space if S is greater than 1, and also if you have an L2 function on your usual L2 function on your fundamental domain F, and then you extend it periodically, then you will get a gamma invariant Hilbert L2 function for this S greater than 1 by this extension method. And gamma, if the Schottky group acts on coverings via you just move them around with your transformation gamma, and under this action chains map to chains, possibly the order gets reversed, and strong maximal chains map to strong maximal chains. And now you fix a covering on your fundamental domain F. Now you have this operator from the previous paragraph section that we had with the matrix AUV. U and V are from those patches of this covering U, and you have this kernel which is made, well, doubly gamma invariant. So you sum over gamma and delta in gamma and multiply every x with gamma to the -1, every y with delta to the -1, and written out this becomes this big function here where you have the distance and the indicator functions and the matrix elements, and this gives you a, we call this a Taibelson-Vladimirov operator with the usual way, this kernel function times f of y minus f of x integrated over dy with this new kind of integral. And we could again define the degree as before. Everything is gamma invariant, and if the matrix has 0 diagonal, then this will depend actually only on U if x is in U. So we have degree, and this should remind you of degree of a vertex in a weighted graph, right? We'll come to this later. Again, we have the Zuniga type inequality, which just says that your operator that we have is bounded, and the bound is explicitly given. What you get more, you get extra, the weight of U, the volume of U, but also this weights m gamma to the -s summed up. This sum converges, right? And f is a gamma invariant test function on omega. So if the matrix A is symmetric with non-negative entries and vanishing diagonal, then and alpha a real number s greater than 1, then the operator is a self-adjoint bounded linear operator on the function space of gamma invariant functions on omega L2. And we can construct wavelets. We've done this before just on the set F, and now we make everything gamma invariant. This is this usual extension here, what is written down there. There's big psi, and then you have a small psi, and then you normalize it and take the index gamma upstairs, normalized by dividing by the S or L2 norm of this function. And we can state our theorem for, so alpha in R S greater than 1, fix a vertical covering of our fundamental domain F, take our matrix symmetric non-negative entries and a diagonal vanishing, see a strong chain of admissible coverings of this fundamental domain such that our fixed covering U is on top and C is maximal with this property. Then the gamma invariant wavelets together with the functions coming from eigenvectors of the Laplacian, graph Laplacian of the matrix, where the matrix entry is in the diagonal 0, and AU times the distance between U and V to the power of alpha, normalized so that's such that the norm is 1, are an orthonormal basis of this function space of invariant L2 functions on omega, consisting of eigenfunctions of our operator. Proof, same way it works. And then we can come towards the Cauchy problem on Mumford curves. So you assume again that A is symmetric, non-negative entries, diagonal vanishing, alpha in R, S greater than 0, and our function, so superscript gamma, so the invariant continuous functions, they form a closed subspace of all continuous functions on omega with respect to any norm for which the big function space is a Banach space. One can prove this, and then you get that our operator epsilon del d alpha with alpha in R generates a strongly continuous positive contraction semigroup exp TED on this restricted invariant function space. And we can formulate the Cauchy problem again as before, but you replace, replace the function spaces. We had before just functions on F, but now they extend them to gamma invariant functions on omega. And again, we have a heat equation on the Mumford curve because everything is gamma invariant, and we have a Feller semigroup, and that means we have a p-adic diffusion process on X attached to this pseudo differential equation. Again, we have our measure, which makes a Markov process, and the paths are right continuous, have no discontinuities other than jumps. And this comes again from convolution with respect to the y variable for this now doubly invariant function coming from the heat operator. And so far, we have had arbitrariness. We didn't really use it. We just used the covering, and we have vertices with edges, and they somehow they do reflect the structure of the curve, the combinatorial structure of the curve. But now we want to have everything canonical. That means the freedom was in the adjacency matrix. We want now the adjacency matrix to be the combinatorial adjacency matrix of the reduction graph associated with this covering of X. So each patch is a vertex, and the intersection is any two, if they intersect, are a circle, and these form the edges of the graph associated with the Mumford curve. So you are jumping around between patches on the Mumford curve if you're jumping around along the graph. So this is again gives you the canonical heat operator di with this particular matrix A. And further, because there's another freedom in the choice of the fundamental domain, we will choose it in such to be inside OK, the unit ball, and with maximal volume possible among such fundamental domains inside OK. Then our theorem is if you vary the curve in families, then the spectrum is such that the smallest eigenvalue, let's see, the largest negative, yeah, so with the smallest absolute value eigenvalue of these canonical heat operators can become arbitrarily small. So if technically mg of g, so small g is the genus, is fixed, and capital G is the stable reduction graph in the set of isomorphisms and classes of Mumford curves having these combinatorial data. Then for every epsilon, this moduli space or families of functions of spaces of curves contains a Mumford curve such that the spectral graph is smaller than epsilon. So I didn't say what stable means last time I did. So a connected graph is stable if no vertex has degree equal to 2. So if you play around with the coverings, then that changes the graph only by subdividing edges. But what you do also is you change the graphs. You have a family of curves having you fix the graph, but you've changed the curve such that more and more edges or less and less edges get subdivided. An example is the case of Tate curves. These are genus 1 curves, and they're always of the form k times modulo a cyclic group Q generated by Q. Q is a number with absolute value, with p-adic absolute value smaller than 1. In this case, we take p to the power of minus n plus 1 over e you have to have because of k. And this is a Tate curve. And a covering is given by taking the fundamental domain that we're looking at is an annulus, to just have a disk with one hole centered in 0. And the covering is just by circles. It's a any annulus is a k rational point of an annulus is a disjoint union of circles where the radii vary, circles centered in 0. And the degree we'll write with index q instead of the group generated by q. And the theorem is that the degree is just a product of something that depends only on the patch ui or I and on alpha, and then SQ of S. So SQ of S is just, you have a sum of geometric series. This comes from, well, calculating the degree or the integrations that you have, everything summing over group elements, but you have just one element that generates the group, so that means you get geometric series of powers of Q to the power of something, either to the S minus 1 or just alone. And the part C, the other factor, just is that comes from the degree. So this is the graph. Just each vertex just has two neighbors. So you have adding up 2 degrees, and this is the sum that you have always, 1 plus or this plus times this. And here you have measures of sets and distances of those patches. You have 3 cases that you've decided. That's why you have this bracket. And alpha is real and s greater than 1. So you can explicitly calculate an eigenvalue, a kind of eigenvalues. And the degree eigenvalues can be explicitly calculated in the case of Tate curves. What you first of all observe that if s goes to infinity, this part here with s minus 1 and so on vanishes in the limit. So you get this. You can approximate your degree with using this. And what I have to look into, I'm not quite sure, because I don't know how to compute the eigenvalues of a general ring graph with edge weights. But for this one, I was able to do it. So the simplest case, you just have 3 vertices in a triangle, and the weights are given by, the distance is either alpha is 1, and the distance is just either 1 or p to the minus 1, depending which circles you take. And for this, I could, the Laplacian of this matrix has these 2 eigenvalues, minus 3 and p minus p plus 2 over p, and the other one is 0. You don't want this. So and the degrees explicitly for large S are these rational functions in the prime P, and you observe that only the first one tends to 0, all other tend to 1, but they're smaller than 1. And the previous one, okay, you have this minus 3, its absolute value is big, but this one also tends to minus 1. So this U0, this is responsible for the smallest absolute value of the eigenvalues. It can be arbitrarily small, and it's always smaller than the eigenvalues that come from the graph structure. So the degrees, they always are responsible for the spectral gap. And the question is it always true for Mumford curves that the Laplacian spectral graph of the matrix B alpha tends to 1 if p goes to infinity? And another question that I ask is, does there exist a Mumford curve of genus G greater or equal than 1 such that the spectral graph gap of the canonical heat operator equals the spectral gap of B alpha? You see here in this Tate curve case, this was not the case because the U0 patch wins, but not with the eigenvalue of the graph itself on the curve. These are absolute value too big. But if you have a general higher genus curve, the question is, can you construct something where the graph eigenvalues win this battle? So conclusion, we have a p-adic dictionary, and this yields the spectrum of heat operators on Mumford curves via graph Laplacian eigenvalues. And also we have the degree eigenvalues of these heat operators. We have double invariant heat kernels for Mumford curves, and the Cauchy problem for heat curves, heat equations on Mumford curves is settled. And we ended with some questions about the relationship between the spectrum of graph Laplacian and heat operator on Mumford curves. Acknowledgements. I thank Wilson actually for his idea that he published on p-adic heat operators on graphs, and David for some discussions that we had which were unrelated but which led to the ideas presented here. And here's Wilson's paper, and this this presentation here is can be found on the archive. Yeah, thank you.
Thank you, Patrick. Very nice stuff. Congratulations. It's a very interesting work. I have many questions. Let me begin by asking you about the construction of wavelets that you presented in the first part of the talk. It seems that this construction works on an arbitrary p-adic manifold. Have you checked this, Patrick? Because this is important.
Let's see, where is it? Here they are.
The construction, the construction of wavelets that you presented in the first part. It seems that this construction works or can be carried out on any p-adic manifold.
Well, it's a local construction.
Yeah, of course.
Yeah,
for that reason, I'm thinking that it's possible to extend this to
Yeah, so you have a local construction, meaning that you have it's supported on a local piece, on a small ball or a small set. You have what you need is characters. Well, you can take them locally. The characters. If you have locally inside K, inside a local field, you have to have a patch inside a local field. And then you have to prove these vanishing integrals if you want to see something useful. At least the first lemma should.
But in principle, it is possible to extend this construction to at least some p-adic manifold.
I would think so, yes.
Okay, that's an interesting problem.
But the manifold has to be locally inside a locally compact abelian group. You have to have a Haar measure from somewhere.
Yes.
Yeah.
Okay, but another question is the operator d alpha. The operator it seems to me that the operator d alpha sub AU, the operator is not pseudo-differential. It's just an integral operator. In addition, it seems to me that this operator is completely different from the Tylerson-Vladimir operator.
I'm sorry, I didn't quite understand acoustically. I didn't quite understand.
Sorry. My first concern, or my first question is that this operator, d alpha AU, is not pseudo-differential.
Is not what?
Pseudo-differential. I mean that this operator can be represented as at least locally as a pseudo-differential operator.
Oh, what is definition of pseudo-differential operator?
Pseudo-differential is that the image is computed by taking the Fourier transform, multiplied by a simple, and taking the inverse Fourier transform.
I'm sorry about that. Yeah,
No.
This is a misunderstanding of notation of definitions.
No,
it's not. It can be diagonalized by the wavelet. But wavelet transformation diagonalizes, but Fourier transformation
doesn't. That's important.
Fourier transformation does not.
Yes.
Fourier.
Yeah, it's not pseudo-differential. Another important thing, Patrick, is that this operator is not really a generalization of the type of Vladimir operator. It seems, but that's not the case. The reason is that these operators, the Tylerson and Vladimir operators, are basically defined on a subspace of L2. And these operators can be defined on L rho for rho between 1 and infinity. Because the kernel is an integrable function.
I see.
So these operators are not really types of bladder operator. There is another paper where I introduced this type of operator, but these operators are not. Are not generalization of the types of Vladimir operators, because these operators are essentially defined in L2, and this operator can be defined in L row, because the kernel is integrable.
Yeah, for any row.
For any row between 1 and infinity. So this is a more general object. Okay.
Oh, okay. What should I call it then? What's the name of these?
I'm gonna please remind me. I'm gonna send you a paper where we introduce this operator. But this is just an integral operator. Okay.
It's just an integral. Okay.
It's an integral operator. Okay. Now, one interesting thing, Patrick, is that at some point you need a weight. I don't remember the page, but you need a weight. This is very interesting to construct a norm. And the weight that you use is exactly the way that we use, or I use to construct the theoretic version of the sub. This weight, the weight exactly. This is the weight that we need to construct a sublet type operator, a sublet type space. So, you see, it's very interesting, and it seems to me. Could you please show us the definition of the norm? The norm. After this slide, you introduce a norm. There is a norm. What is the norm? This norm.
Yeah.
It seems that this is a kind of sublet, or a kind of. The space LS. It seems that it's a kind of sublet space in your framework. Okay.
Okay.
This is really interesting. Okay. This is really. Please remind me. I'm gonna send you some reference for this. Okay.
Okay. Thanks.
Okay. Another interesting thing is in page 51. I think it will be page 51. Yes, this theorem. Okay, here you have a connection. You show a connection between the geometry of the manifold and the spectrum of the operator. But honestly, it is not clear for me what is the geometric implication of the spectrum of the operator d alpha. In other words, if you know the spectrum of the operator d alpha, what kind of information you get about the geometric object? Can you, for instance, use these operators to study Mumford curves, to say something about Mumford curves?
Well, I don't know. I don't know yet.
No, I know that this is a difficult question. Okay.
Yeah.
But this is this is extremely important, because if you can say you can have a result in this direction, then this result becomes very relevant, because you can use this machinery to do some geometric calculation. Or to get some geometric information. Okay, but this is a very nice work. Okay, I don't have more comments. Okay, and now for the audience, are there comments, questions?
I do have to go, but I want to say thank you. That was really interesting.
Okay, thank you. Bye, Joe. Are there more comments or questions?
No.
Okay.
I really enjoyed the presentation.
Okay, thank you.
I think I understood some of this.
Okay, perfect. Thank you.
I'm sorry. I just wanted to ask. I wasn't able to join the beginning, but I see that you are recording the talk. Can we get the slides also?
Yes. Let me stop recording. Okay, stop recording.